So the next talk is entitled Virtual Elements for the Transmission Eigenvalue Problem. David, please, stage is yours.
Hello, good morning here in Latin America, in Chile. I hope that you're all fine. And thank you very much for the introduction, Stefano, and also thank you the organizers of this conference. Okay, I'm going to talk about present a work related to a virtual element method for the transmission eigenvalue problem. Okay, this problem appears in many years ago, but in the last 10 years or less, there has been presented the numerical analysis, introduced the numerical analysis of this problem. Okay, so I'm going to tell you a virtual element discretization for this problem. Okay, this problem is in collaboration with Iván Velázquez from the Universidad del Sinú in Colombia, and this work has been supported by the ANIT Chile. Okay, can you see the screen? Okay, yes.
David, yes, we can see the screen. We cannot see your face. I don't know if this is intended or not, but it's okay, as you prefer. Okay,
no, just because of the internet, okay?
Oh, no, let me know if you prefer because of the internet is low, then you can put it off, as you prefer. I just wanted to tell you.
Yes, let me know, okay? If you can hear me, well, I can do that like that. Okay, the continuous problem, where we will introduce the outline. It will be the continuous problem where we will introduce the continuous formulation, and we also will present we'll introduce the solution operator to analyze this problem. Okay, then we go to the virtual element discretization, where we are going to consider a C1 discrete space to write the discrete problem and the corresponding discrete solution operator. Okay, then we go to the convergence and error estimate, where we will establish the error estimate for the eigenvalues and for the eigenfunctions, to finish with some numerical tests. Okay, benchmark there. Okay, for the continuous problem, we introduce the transmission eigenvalue problem, is to find the eigenvalue kappa, okay, in C in principle, and two functions T1 and T2 in L2, such that the difference is in H2, which satisfies this system. Okay, we are going to, in this work, we are going to restrict the analysis to the two-dimensional case, and we consider n, the function n here, which is a data here, is the so-called index of refraction. Okay, it's a real value function, and nu is the outward unit normal to the boundary. So this problem can be written in different ways. Okay, considering the system writing a variational formulation for the T1, T2, etc. But there is a formulation of the problem where it is introduced a new unknown which is defined by the difference of T1 and T2, and we can see that as a consequence of the boundary condition, we observe that in U belongs to H02. So we can rewrite the problem and test testing the problem with a test function. We can arrive to the following variational formulation of the problem. Okay, find the kappa, the eigenvalue, which is the important here, and and in this case, the eigenfunction u of this problem, which represents the difference between T1 and T2, which satisfies this variational formulation. So the first observation here is that the eigenvalue problem formulated in this way is nonlinear in terms of the eigenvalue. So we can see here that it is a quadratic, is the so-called quadratic eigenvalue problem. Here we have kappa square, and here kappa power 4, okay? So we have to find a way to approximate, to solve this problem, okay? So we are going to consider a virtual element discretization to solve this. And in particular, what we are going to do is introduce a new variable, okay, in the system, in this problem, to write a linearization of this problem, okay? So we are going to get, in some sense, okay, this is usual in this kind of eigenvalue problem, we are going we have to work with a double size eigenvalue problem, which is linear, okay? So, but it has some difficulties about related to the non-selfadjoint, etc. So here are some references for the which has for numerical method to solve this eigenvalue problem. For sure, this is the first one is the first analysis of the transmission eigenvalue problem, and they propose a C1 finite element method to solve a linearization, but using a different variable. In this case, the author have considered for linearization an additional Laplace problem, and they have written and they have analyzed the system by using a GDs element, okay, a conforming C1 element. So that there are others reference here where they have using non-conforming finite element, and in particular here in the last reference, in this reference we have proposed a virtual element discretization for the same formulation presented in the first reference, okay? So in this work, we are going to consider, in order to analyze the problem, we are going to consider a different linearization in some sense, okay? So okay, in this reference, which we didn't know up to a referee report arrives for this work, okay? There has been introduced this variable, okay? This reference is an archive preprint from 6 years ago, which is not published, okay? And in this reference, a finite element method, conforming finite element method C1 is proposed to solve the problem, okay? Using the GDs element, okay? So the idea here to write the linearization of the problem is to introduce, okay, the variable set, which is defined kappa square u, and testing with and using this new unknown in the system, we arrive to the and testing with adequate function using the boundary condition, we arrive to the following formulation, continuous formulation for the eigenvalue problem. So we observe here that we have now two variables. So this means that it is double size eigenvalue problem, but we observe now that it is a linear eigenvalue problem. So we only have here lambda. Okay, and we observe this, okay, and by linear form, Cesky linear form A and B are defined by this expression. Okay, here in the first part of the of bilinear form A, we have the Laplacian sesquilinear form. Here the L2 inner product, which is derived from the linearization in some sense. Okay, and the left hand side, the right hand side here is defined like this. We observe that the right hand side, the left hand side is self-adjoint, is bounded and elliptic in some sense in this space, okay, which is H02 times L2. So in the following, we are going to assume that n is a real constant to present in the following. So as I have mentioned, we have that the sesquilinear form A is coercive in the product space. This norm is going to be used for the product norm here. Okay, so since sesquilinear form B is bounded, we can introduce the so-called solution operator, which is no other thing that for any data here in H2 times L2 gives the solution of the so-called source problem. This source problem is obtained from the eigenvalue problem, where we have replaced F and G by the eigenvalue times the eigenfunctions on the right-hand side here. Okay, so this is the so-called eigenvalue problem, and we can see that the solution, the eigenpairs of these solution operators are related with the solution of the transmission eigenvalue problem. Okay, it can be easily see that if I have an eigenfunction of the transmission eigenvalue problem, so we have a relation with eigenpairs of the operator T. So to obtain complete information about the solution of the transmission eigenvalue problem, we have to describe the spectrum of this solution operator. So with this aim, we first have this lemma, which is an additional regularity result for the source problem. So we have that there exists S in this interval 0, 1, and a positive constant Cn, which depend on the index of refraction, such that for any Fg in the as a data of the operator, we have that the solution, the unique solution of this of the source problem is more regular. Okay, the first component of the solution is more regular. So we have that U tilde belongs to H2 plus S. Okay, but the second component in the solution of the source problem is not more regular because there is an identity in the definition of the this is the in some sense this plays the role of the linearization. So we have an identity with the data. Okay, so this F is in this source problem is exactly equals to or to Z. So in the second component, we have an identity here, and we get this this estimate. So as a consequence, we immediately have that T is a compact operator, but it is not self-adjoint. So we can use the typical result for this kind of problem, and we have this spectral characterization. We have that the spectrum of T is equals to 0, and a sequence of complex eigenvalues which converge to 0, and they eigenspace lies here in this space. Okay, we observe here that in the case of the eigenfunction of the solution of the eigenvalue problem, here the set is more regular. Okay, because this I have mentioned this before, or because this is an identity in this case is exactly equal to U times the eigenvalue. Now we complete this, the continuous part of the problem. So we have complete information about the solution of the transmission eigenvalue problem. Now we go to the discretization of this by virtual element method. So we observe here that that we have to use in the conforming setting, we have to use a C1 space for the eigenfunction, at least for one. Okay, so we are going to consider a C1 discretization for this. We introduce the usual setting. We are going to consider we want to consider polygonal meshes, and we are going to use the virtual element. To construct the discrete scheme, we first have to introduce some preliminary definitions. First, we split the sesquilinear form A and B. A and B in the element contribution. Here we have moved, since n is constant, we have moved to the Hessian product here, and all the others is just the restriction to the element of the sesquilinear form. So to construct the discrete scheme, in this case, what we need is a discrete space in this continuous space. We have to construct the discretization of the approximation of the sesquilinear forms. We are going to try to write the two sesquilinear form A and B in this way, where A sub h power k is and the same for B will be local forms. Okay, and with this, also with this ingredient, we have to write a discrete solution operator, TH. So to discretize the problem, we consider a C1 space, which has been already used in the past to discretize some other C1 four-order problems. So the space are H2 functions where the B Laplacian is in P2, the normal component of the function is in P1, and the function on the element is P3. So the functions will be continuous on the boundary of the element and also the gradient. So this we see now that, or we observe here that we are going to consider an enhancement technique in order to try to approximate, to construct an ad hoc projections in the L2 setting. We observe here that the P2 polynomial space is included in this space, and the set of linear operators, which are going to be up to after the enhancement technique, there will be the degrees of freedom of the space. So the first set is the one are the evaluation of the functions on the vertices of the polygon, and D2 contains the evaluation, pointwise evaluation of the gradient on the vertex of the function in this case. So once we have the discrete space, here we construct the polynomial projection using the Hessian product from the virtual space to the P2 polynomials. Okay, here we use this is perfectly computable because of the integration by part on the right hand side, and also this bilinear form, this sesquilinear form has a kernel. So the second condition here is to fix an element in the kernel of this operator. So like here. After that, we construct the local space as the enhancement technique in order to compute the L2 projection here, and we glue all together to construct the global space. So what we are going to consider here now as a discrete space, HH will be the product space of this WH, which is a C1 element, C1 space, and construct in order to approximate U. But in this case, we can also use to approximate the other quantity set, the additional unknown, which is equal to is a multiplus of U. So what we are going to do, we can do other choices also here, but in this case we are going to consider to approximate the L2 functions the same space as for the first. Okay, some details on the construction of the for the enhancement technique and the construction of the C1 element can be seen here. Okay, we introduce now the polynomial projection, the L2 projections onto the polynomial of degree m in this case, and we assume that we have two Hermitian positive definite bilinear forms, local, which scale like the sesquilinear form A in this case. So we have the Hessian and the L2 inner product. Then, as soon as we have the approximation, we are going to build the global sesquilinear form A in this way and the global sesquilinear form B in this way. So I remember that the discrete space is the same for both variables. So using the virtual element framework, we introduce the local sesquilinear form as the consistency part plus the stabilization part for A1 and A2, and also and here we only replace the functions by the standard projections in each term. We have here the usual consistency and stability properties for the BEM for these local sesquilinear forms. This is going to be used in the error analysis. And with the sesquilinear form, the local one, we construct the global one, and with the global one, we define the discrete eigenvalue problem, which is written in this way. We immediately have, because of the definition of the sesquilinear form A, we immediately have that the sesquilinear form A is coercive, so we have this lemma, and as a consequence, we can introduce the second ingredient here to analyze this kind of problems, which is the discrete solution operator. Here, the discrete solution operator is given H2 functions times L2. This gives the discrete element in the discrete space as the unique solution as a consequence of the coercivity of A of this source problem. So in this case, we also have that the discrete solutions of the transmission eigenvalue problems are related with the eigenpairs of the discrete problems. Okay, now for the convergence and error estimate, we are going to consider the usual assumptions for the mesh, which is the element is star shape, and we have that the ratio of the shorted edge is comparable with the diameter. As a consequence of this A1, in this case, we have the polynomial approximation in this case, which is the proposition there, and we can see, we can prove, or it has been proved, that we have an approximation in the virtual space for an interpolar in the virtual space. In this case, the proof can be seen in particular in this second reference for the space. So as a consequence of this, we have the convergence in norm, okay, for the solution operator. So we can prove that the difference t minus th fg is less than this quantity. Okay, so using the additional regularity for the source problem, in this case, we observe here that this is the source problem, the solution of the source problem, using the additional regularity and the interpolation, the proposition that I have mentioned before. So we are able to prove that the convergence in norm in this case of the th to t. Okay, since the problem is not self-adjoint, we have to also deal with the joint continuous operator and the discrete one. So, and in this case, we can also prove that the convergence in norm in this case for the adjoints. So as a consequence of this, we have immediately that using using the argument in this reference, we have convergence for the eigenfunctions and a double order for the eigenvalues for the problem. In this case, we have mu here. The mu here represent the eigenpairs of the transmission, the solution operator, but it relates immediately to the solution of the transmission eigenvalue problem in this way, in this written in this remark here. Okay, because as I have mentioned before, the solutions are related. Okay, now I go to the numerical results section. We consider three configurations for the numerical results. Here we consider a square domain, an L-shaped domain, a circular domain with different mesh for each domain. Okay, to complete the stabilization, we are going to use this one correctly scaled in order to consider the stabilization. In the H2 case, we have to multiply by H minus 2. For the L2 part, we have to multiply by H squared, and everything works here. For instance, in the first case, we consider a constant index of refraction, and we see here a perfect H2 convergence, a double order for the eigenvalue approximation. Here we compare, for comparison, we have written here some reference. Here we consider the same result, the same problem, but with the index of refraction 4. Here we get a mix between a complex and real eigenvalues. Here again, a double order of convergence for squares domain, square meshes, hexagonal meshes, and Voronoi meshes in this case. Here a non-constant. Here we use a non-constant index of refraction, which the analysis follow the same lines. Here again, a double order of convergence. Here a circular domain, again the double order, and finally an L-shaped domain. Here we have a singular solution here in a non-convex domain. So we here see a double order of convergence in terms of the Sobolev regularity of the eigenfunction in this case. Okay, some pictures here of the eigenfunctions related to this problem. Okay, thank you very much.